This one is presented as a word problem. You have a spherical balloon that is being inflated at 10 cubic centimeters per second, and you want to know how quickly the radius is changing when the radius is 7 centimeters. First of all, maybe let's just think about this a bit. You're inflating this balloon at a constant rate. The rate of change of volume is constant. But that's not going to translate to a constant change in the radius. As the balloon gets bigger, it's sort of easier and easier to find space to put that extra volume without increasing the radius by very much. Or said another way, small increases in the radius will give larger increases in the volume when the radius is already pretty big. So how can we actually see that mathematically? Well, what gives a lot of students trouble with a problem like this is that it's not set up in this kind of abstract mathematical form. So let's practice actually putting it into such a form. Now we're dealing here with a spherical balloon, and we're talking about its volume and its radius, so you need to know how the volume of a sphere is related to the radius. And so this just comes from geometry, that the volume of a sphere is 4/3 pi r cubed. So that uses up that sort of piece of information, that the balloon is a sphere. It's being inflated at 10 centimeters cubed per second. So if you look at the units of this, that's units of volume per time, and that acts as a little bit of a hint that this is a statement about dV dt, and says that dV dt is 10. And you have to be a little bit careful sometimes about the exact wording, because if I had said, for example, it was being deflated at this rate, well then something that's being deflated is losing volume, so then I'd have a negative sign here. It'd be negative 10. But in this case it's positive 10. And then what's the actual question? Well, the question is, how quickly is the radius changing? So that's really asking you to find dr dt, and not just dr dt as a function, but when the radius is 7. And so what I've done is I've kind of gone through sentence by sentence, and I've taken all of the information in the problem and rewritten it kind of mathematically here, so that now if you were to just completely get rid of all of the blue text, you'd still have enough to actually solve the problem. Right? And that's how you know that you've already sort of written down enough of the math. Well, we want dr dt. We know dv dt, and we know how v depends on r. So since I have v as a function of r, maybe the easiest way to do this is as dv dt is equal to dv dr times dr dt. Another option would be to solve this equation here for the radius in terms of the volume, in which case you'd be able to find dr dv, the derivative of the radius with respect to v, and write a sort of similar equation. But this is going to turn out to be quite a bit easier. So, what are the pieces that we have? We know that dv dt is 10, so I can just fill that right out. And dv dr just means the derivative of this equation, treating r as the variable. So that's just going to be, well, it's 4/3 pi times 3r squared. I'll leave it like that for just a second. Times dr dt. Of course, that 3 and that 3 cancel, so you just get 4 pi r squared for dv dr. But now I want the radius to be 7. So in fact that's 4 times pi times 7 squared times dr dt. So all of this together is equal to 10. And since I want dr dt, we'll just divide both sides by this whole quantity. And so you get that dr dt is equal to 10 divided by 4 pi times, well, 49. You could simplify that a little bit, but that's basically it. And actually, if I were putting units on this, the units would be centimeters per second. So there you go. That's the rate of change of the radius with respect to time.